we went through 3 gas laws originally, Boyle's, Charles, and Gay-Lussac's, and we realized those are all combined in the combined gas law, and that's what we've been using to solve those problems. Those happen at an initial condition and a final condition. So we have changing conditions, and that's our combined gas law, which is P1, V1, N1, T1 equals P2, V2, N2, T2. So we have initial and final conditions, condition 1, 2, before and after, however you want to learn that. Now, in addition to that, we learned the ideal gas law, which is if we know all these variables at one condition except for one, we can solve at one condition, and that's PV. PV equals nRT. So when do I use which equation? This is where our chart comes in handy. So I'm going to fill out these 2 charts, pause the video, and you fill them out too. We have 2 problems here. In one, I'm using the combined gas law equation, and the other one I'm using the ideal gas law equation, and I have to figure out which one. So fill out your chart. Okay, so once I have these in my handy dandy boxes, I can see that everything here is at only one condition, and that would be the formula PV equals nRT. And what am I solving for? I'm solving for pressure, so let's get pressure alone. I'm going to divide by volume, I'm going to divide by volume, and that's going to give me P equals nRT divided by V. Okay, so that goes right here in your formula rearranged, which you need for credit. Okay, nRT divided by V. Okay, now my other problem has an initial and a final condition. Now the first thing to notice on both of these is I changed my temperature to Kelvin, changed my temperature to Kelvin. This has a pressure of this millimeters of mercury at 40 degrees C. These are happening at the same time. It has this pressure at this temperature. There's my pressure at the temperature changed into Kelvin. And then it says, what is the temperature, question mark temperature, at standard pressure? And then there's 340 K here. I think I actually put the answer right there, because sometimes I put them at the end instead of the bottom. But in any case, that has nothing to do with the problem right now. At standard pressure. So what's standard pressure? Well, it's 1 atmosphere, which is the same as 760 millimeters of mercury. Now my first pressure was in millimeters of mercury, so I picked the one that was in millimeters of mercury. Notice I have 2 conditions. Things changed. What is the new temperature at a different pressure? Okay, so that is my PVNT equals P2V2N2T2. Okay, now I don't have volume and I don't have moles. We assume they're constant, so I cancel out my volume, I cancel out my moles, cancel out my volume, cancel out my moles. And what am I solving for? I'm solving for T2. So that's actually at the bottom. Now, just a little trick. Remember, it doesn't matter if you put this in 1 or 2. So sometimes if you flip this, it'll work, but it won't help you here. But in any case, I digress. Okay, so we're solving for T2. Not only do I need to get T2 alone, but it has to be on top. Remember, the easiest way, what did I do here? I just moved my volume kitty corner, right? Across and down, diagonally across that equal. So I can move anything. That's what algebra does when I just have a ratio there. I can just move that to the top, and I get P1 T2 T1 equals P2. Okay, but I need T2 on top. It is, and now I need it alone. So I can move my P1 down here, and I can move my T1 up here, and that will give me, T2 will equal P2T1 divided by P1. So that goes right here. That's our T2 equals P2T1 divided by P1. So now I've rearranged the formula. The last thing to do is just to plug in your numbers, right? My pressure is what I'm solving for. My moles is 40.0 moles. Okay, my R. What is my R? Where did you get that number? Well, R is the ideal gas constant. It's a constant number. It doesn't change. I only gave you the one that goes with atmospheres, and that was 0.0821. Liter, atmospheres, Kelvin, mole. And this is not a formula. These are all the units that go with that number. Okay, so let's plug that in. 0.0821 liter, atmosphere, mole, Kelvin. And then my temperature is 298 Kelvin. And remember, our units can all cancel. My mole on top cancels with this guy. My pressure cancels with this guy. Or I'm sorry, my temperature cancels with that guy. And right now, it's telling me that I have liters per atmosphere. So I know that I did something wrong here. What did I do wrong? Well, it's nRT divided by V. So I need to also divide this by my volume, which is 4.50 liters. And now my liters will cancel out, and I'm left with atmospheres. Okay? Okay, so I wanted to show you that so you can see if you do all your units and cancel them out, you can see when you have a problem. And indeed, I didn't have my volume in there. I knew I was missing something. That's how it works. If you plug that in your calculator, 40 times 0.0821 times 298 equals divided by 4.50, you will get this answer. And what are my units? Well, the only unit left is atmospheres, and that's great because I'm solving for atmospheres. I have 2 significant figures, 3 significant figures. Oh, actually I have 3 sig figs, 3 sig figs, 3 sig figs. So my answer should be 1, 2, 3 significant figures. The 4 doesn't round it. It should be 217 atmospheres. Okay? So now I've got kind of a mess going on here. I want to rewrite this. T2 equals P2T1 divided by P1. I'm going to plug that in. Temperature 2 is what I'm solving for. Now my pressure 2 is what's on top. This is my pressure 2. Remember, initials 1, finals 2. So that's 60 millimeters of mercury times my temperature 1, which is 313 Kelvin, divided by my pressure 1, which is my initial 699 millimeters of mercury. And my millimeters of mercury cancel out. When I solve this, my answer is going to be in Kelvin. And my guess is that was the answer, 340. Let me double check on my calculator. You do so as well. If you don't check this on your calculator, you won't know if you have a calculator problem. And at the beginning of this unit, half of you, in general, that's what I usually have calculator problems. Please check that you can put this in your calculator and get the same answer. Okay, and just as I suspected, that was the answer. You got a rounded answer like this. I have 1, 2, 3, 4 significant digits there. I have 1, 2, 3 significant digits in my number, and this was a given, so we don't care about that one. We look at the numbers they gave us. 60 is exactly a flat out number. We don't use those in our sig figs. So we have 3 sig figs. In order to make that 3, I have to put a decimal there. Okay? So what I have for you is 2 problems. One's going to be the ideal gas law and one's going to be the combined gas law. I have them side by side so you can compare and contrast and see difference. I have it again. Okay, and then I have number 7, which is converting grams to moles, and then number 8, that is one of your gas laws where we start with grams. Remember, you have to convert it to moles. You need to show your setup. That means just show me the rearranged equation. Okay, and then I have your answers down here. Oh, for B, let's go back. I missed that one. It's 217 atmospheres. Now, we run reactions a lot of time in a closed vessel, so we need to do these calculations to see if they will explode. The cylinder that they're running a reaction in will hold 250 atmospheres at the highest, and then it will explode. Will this cylinder explode? Well, it explodes at 250, and I'm under 250, so no, it will not explode. Okay? And that's some of the reasons why we do these.